Hi, I'm Carlton Coffrin. In this video, I'll give you a brief introduction to the Code2 open source solver that I've been developing for APRA-e's grid optimization competition. This talk has three core goals. First, I'll begin with a brief introduction of who I am and what my involvement in this project is. Then I'll give an overview of the Code2 algorithm that I've been developing and has been released to you upon request. And then I'll give some pointers to start looking into the code if you want to understand the algorithm in more detail or potentially modify it for your own needs. So first off, who am I? I'm a computer scientist who specializes in optimization algorithm development. My PhD advisor is Pascal van Hentenryck. You've probably heard of him. My specialty is in power systems optimization. I've developed things like the LPAC approximation for the power flow equations, the QC relaxation of the power flow equations, and I've been quite involved with AC-OPF benchmarking libraries to evaluate these different types of formulations. I'm currently a staff scientist at Los Alamos National Laboratory in a team called the Advanced Network Science Initiative. We do all sorts of different optimization and machine learning tasks across different infrastructure systems. So what is my role in the grid optimization competition? So I'm associated with the organizational team, so that's nominally led by PNNL. Usually I'm kind of working behind the scenes. My primary role is to develop baseline algorithms for the competition problem with the plan that all of the code I developed will be open sourced at the end of the competition on lanl-ansi's GitHub account. I also provide some data analysis and validation, primarily from a competitor's perspective, so I'll take a look at the data sets and analyze different ways of performing solutions and then provide feedback both to the competition organizers and also the teams that are providing that data. So it was decided that I should release the Code2 part of my solution a little bit early so different teams could take advantage of a baseline solution for that. So that's the purpose of this video. I should note that this current implementation is still very rough around the edges. There are many improvements that can be made, and it's my intention to continue to make improvements to it and make further releases of the software as the competition goes on. We're currently in the process of getting that released on github.com, so you can access kind of a live version of the solution too that I'm developing. But for now, just to get it to you as soon as possible, we're distributing it via email. And I have to note that access to the code for now is really limited to those who are registered and competing as part of the Go competition. Once it goes open source, it's going to have a very flexible license that anyone in the world can have access to. So first thing to know is the implementation language that I've been using. So I'm a big fan of the Julia programming language. If you haven't heard of it, it's a fairly new scientific computing language that strives to be the best of MATLAB, Python, and C. And it's free and open source, which is a big advantage over MATLAB, for example. It's very popular at Los Alamos. One of the things that's made Julia particularly popular in our group is this JUMP mathematical programming framework that's built on top of Julia. It is similar to AMPL or GAMS if you've used either of those, but in Julia, and it's free, and so that's great. One of the activities that I've been doing at Los Alamos over the past couple of years is developing different infrastructure modeling packages inside of this Julia ecosystem. So you'll see things like infrastructuremodels.jl, powermodels.jl. These are developed by me and other folks at Los Alamos National Lab. And naturally, the algorithms that I'm building for this competition are built on top of powermodels.jl. My motivation here is to kind of extend the problems we can solve in power models to include security-constrained optimal power flow. Okay, so that's enough background. Let's do an overview of the Code2 algorithm that I'm releasing now. So first thing to know is that this is not a super awesome state-of-the-art Code2. It's really just a very reasonable baseline heuristic that I've been using as a foundation for playing with different kind of ideas. The algorithm I'm releasing now really focuses on scalability because we want to be able to produce reasonable solutions on those large networks with 10,000 buses or more. It's my expectation that the top entrants in this competition will have much better ideas than what is in this code, but I do find that this is kind of a reasonable place to start for getting a solution 2 printed. In this talk, I'm going to assume you have a detailed understanding of the problem specification. If not, go read it. But at this point, I think everyone should have a pretty good understanding of what the inputs and outputs are and what the requirements of the solution 2 are. I will also assume you have a basic understanding of power network optimization, so like AC power flow versus AC optimal power flow. I'm not going to have time to go into that in any detail. Okay, so let's talk a little bit about what is the challenge of producing a solution 2 for this competition. So at kind of its core, the idea of solution 2 is that you want to demonstrate an AC power flow solution for every contingency and kind of show that your solution 1 was secure across all these contingencies and there's a reasonable power flow that would resolve after the contingency has occurred. So this would inspire, a very simple code 2 that would be really great if this is all we had to do, which is for every contingency, solve a classic AC power flow, and then just like write out the solution to that power flow to solution 2, and then call it done. Unfortunately, that simple approach doesn't work, and it's for the following reasons. So the traditional AC power flow has a slack bus in it, which is used to compensate for any mismatch in the generation that's specified in the power flow and the amount that is actually needed to solve the equations. So this slack bus approach is not a good approximation of the linear response model that is in this competition formulation. So that's the alpha parameters, which are controlled by one parameter called delta. Another challenge you'll face is that for a solution to be feasible, you need to obey all the variable bounds. So this is like the active power bound, PG, the reactive power bound on generator, QG, the voltage magnitude at the buses. If you violate any of these bounds, your solution 2 will be marked as infeasible and you'll get a crazy high penalty for doing that. And there's no easy way, at least that I know of, to enforce these kind of bounds in an AC power flow because it's a feasibility problem. It's not an optimization problem. Now, the most kind of direct mathematical way to address this is that you encode a more accurate version of the recourse model into your code 2 solution. But if you look at this, it's a challenging non-convex disjunctive type of problem, and there's a number of encodings discussed in the competition problem specification document, but I don't know of how to scale any of those up to a 10,000 node network. So we fall back on a couple of different ideas to kind of make something that's simple and reasonable for code 2. The first thing is that we're not going to have a slack bus in the traditional AC power flow sense. Basically what we're going to do is we're going to add a new linear constraint to the power flow problem, which will control the active power that goes out of all the generators. So in this sense, if we're not hitting any bounds on the active power of the generators, we can exactly model the linear response using this linear equation in an adapted for the competition AC power flow. The second core idea is that enforcing these variable bounds via the pure disjunctive form is not going to be very scalable. So what we're going to do is a kind of greedy approach, which is often called bus switching in commercial tools. And it works along these lines. So you solve an AC power flow ignoring all the bounds, and then you go through and you start checking, did any of these bounds violated in any one bus or generator? And if it is, you're going to basically fix that variable to its upper bound or lower bound, depending on the direction of the violation, and then you're going to resolve the power flow. And that's why it's called bus switching, because basically you're switching the bus from a dynamic variable to a fixed variable. So you just repeat this process until all the bounds are satisfied or an iteration limit is reached. So in some sense, this is like a greedy way of handling the disjunctive constraints. Finally, a key piece of the code 2 is a post-processing step. So just before writing out the solution 2, all of the variables will be adjusted to be within their bounds. And so this will ensure that the solution 2 is always feasible by the evaluation code, but it possibly can cause a lot of power balance penalties. So if you look at the output that's generated by the solution 2 code that I've developed, at the very last step it outputs like a huge matrix of data that reports on how much adjustments had to be made to the solution, the power flow solutions to kind of make the solution 2 feasible. And in an ideal situation, 0 modifications will be made and you'll kind of have 0 penalty coming out of the evaluator. So those are the core basic ideas. Let's talk about the algorithm in a little bit more specifics. So there's a lot of machinery around the solution 2 code to kind of integrate it with the platform and run it in parallel and these other things. But the core algorithm is this function called run fixed-point pf v2 underscore 2. So clearly this is like one of many, many algorithms I've tried. And inside of the core code that will be released in full at the end of the competition, there will be many other variants of this particular problem. So let's go through, what is the core of this function. So the first thing it does is it tries to compute a good guess for what the delta parameter should be. Now this is interesting because as the generators are responding on active power, they start hitting their upper bounds, and then the delta parameter as you ramp it up doesn't give you as much power as it does before you hit those bounds. So it's actually a little bit tricky to figure out, well, how big should delta be such that you balance the power that was lost from, say, losing a generator. So there's a function called apply PG response, which reasons about these upper bounds on the generators and then says, okay, I think this delta is a reasonable value to start with. So we compute this reasonable delta, and then we run an initial AC power flow. So the core function that runs the AC power flow is called run fixed pf nbf rec2. Again, this is just one of many formulations in the master code, which has lots of different variants. But if you look into that, you're going to see it's a pre-traditional power flow formulation with these basic modifications for fixing values to specific, fixing terms to specific values, or setting this linear response model based on delta. So now we have this is kind of like a basic power flow. While then we'll start checking, are any of the values out of bounds, and then we'll start fixing things. So first scan over every quantity that could be out of bounds, check if it is. If it is, set it up to be fixed in the next power flow run, and then we'll run our revised AC power flow, and it's just another call to this same function. And then we just repeat that over and over again until you either hit an iteration limit or you can detect that some kind of cyclic behavior has occurred. So you'll see in this function there's a parameter called iteration limit, which initially is set to some large value, and then in another part of the code it's set to a default value of 5 currently. But you can play with that if you want to see how it changes runtime or solution quality. There, you'll see when you look in the code, there are various fallbacks in case any one of these steps fail, that it will output something, because any reasonable setting of the voltages is better than failing entirely. So there's quite a bit of logic in there to handle that. And then finally, this post-processing step, which will correct all the bounds so that the solution 2 is feasible, is called correct contingency solutions. So just a couple remarks about this particular implementation. there is no bus shunt optimization. So if you look at the formulation, one of the nice features is that you can control the bus shunts in the second stage to potentially improve the voltage profile. My experience is that just running one AC optimal power flow in the second stage for each contingency was taking way more time than was feasible for the really large cases. So at least in this current release, no bus shunt optimization at all. Another important thing to note is obviously this solution relies heavily on power flow studies, and it solves those power flows to a pretty high level of accuracy. So like the bus mismatch will be 1e minus 6 or 1e minus 8. So it's very important that the solution 1 has like minimal violations on the power balance. So the very first thing the code will do is check, like, is solution 1 within bounds? Does it look like something that's kind of reasonable? And then it'll check, is the power flow equation satisfied to a fairly high accuracy? And so this function compute power balance deltas computes those imbalances, and then you'll see there's a little check around this function call which says I give up if they aren't balanced to a reasonable level. So the code can run in parallel. Of course, that's quite essential to getting the runtime down. Currently, what it does is it looks at the number of threads that are available on the current system, and it will use either 75% of those threads or 12, whichever is a smaller number. I selected 12 after doing some studies on different computers and seeing that there was really diminishing returns after 12. Depending on how many sockets there are in your machine, you can easily congest the communication bus. And so 12 seemed to be the sweet spot of performance improvements that I saw. In any case, there's this parameter called max threads in the myjulia2 code, which allows you to change what the maximum is. You can play with that if you want to test if there's some advantage on a particular piece of hardware. I should also note that like all of the NLP models and all of the really heavy lifting from a numeric standpoint is being done here with JMP and IP-opt. So kudos to the developers of those tools. They work amazingly well. And given that this is like a very flexible code and that isn't super specialized, I'm really impressed with the performance that we have using those tools. So here's some basic runtime statistics that you can use just to test that how it's working on your computer is roughly the same as how what I'm seeing. So the first thing to note is that the performance you get out of the solver can vary a lot based on your solution 1. If you're producing solution 1s that require a lot of bus switching, it's going to take more time to solve. If they magically don't require much bus switching, it can go much faster. In this particular experiment, I was running on a computer with two 2.1 gigahertz Intel CPUs and 120 gigabytes of memory, and it was running with 12 threads in parallel. So for the 500 bus case, one of the open access 500 bus cases, it was solving solution 2 in about 1 minute. For the 2000 buses, we're talking about half an hour. For many more contingencies, so like the 3000 bus with 6000 contingencies, twice as many as this previous example, it takes about 1 hour. Clearly the number of contingencies has a huge impact on how long it takes. And then just as a kind of a extreme point, if you're looking at the 10,000 node network that was recently released as part of trial 1, that can be solved in about 8 hours. So there's definitely a lot of improvements that can be done in terms of runtime performance. For those of you who maybe develop dedicated power flow algorithms, these are quite long runtimes. And so there's lots of room for improvement here. Again, this is supposed to be just like a baseline algorithm. How can you get started running the code? So first thing you're going to need is Julia. So you can go to julialang.org and install version 1 or version 1.1. They both seem to be quite reasonable. The code is working in both. Either one should work. So you're going to get a zip with the source code just sitting in there. if you go into that root directory, you can start kind of installing or setting it up, that software. So the first thing you want to do is start Julia with this command -- project and then dot for the current working directory. This project feature basically allows you to load all of the settings for exactly the packages that I used for testing the software. So it'll know exactly the environment that I had set up. So once you enter the REPL for Julia, you do using package instantiate. What this is going to do is download all of the dependencies that I used for testing onto your local machine. Everything is open source, so there should be no issues there. The next thing is there's this warm-up script which does pre-compilation of Julia packages, which are mostly provided as source, just to get the basic things set up. If you don't run this warm-up and then you run a parallel code, you can have this kind of unfortunate situation where all the threads are trying to build the code in parallel and they kind of clobber each other. So once you've run that pre-compilation step, this testit.jl script will run the solution 2 on a pre-baked solution for the 14 bus case that's provided as part of the competition platform. So you'll see a bunch of terminal output regarding the solution process. Once you've kind of got that basic in Julia test working, you can start to test from the command line. So my Julia2.jl is the kind of front-end executable that the platform will run. Inside of there, it shows you, how the multiple threads get spun up before running the core code. And then testit.sh will run that from the terminal. So you need to be in bash terminal, so that's for like Linux or Mac users. But it emulates exactly the command that the platform is going to run, just so that you can test it's all working. So with that, I have a basic introduction to the code that we've just released. I hope you find it useful, and please feel free to modify it or adapt it for your own needs, borrow ideas from it. I will do my best to answer questions about it, and I may produce additional content to answer common questions that are asked. But just keep in mind that I am one person and bandwidth is limited. I'll get to things as fast as I possibly can. So thank you very much, and I hope you enjoy the software.